Alright everyone, in this video we're going to be covering extreme of a function, especially on an interval, open and close intervals. So in calc, much effort is actually devoted to finding when a function has a maximum or a minimum on some interval, called that interval, let's say I. So we will see a lot of applications of how finding the max or minimum of a function will help us in the future. I'll begin this section by first defining a couple of things. So first of all, let f be defined on an open interval, actually not even open, on an interval, could be open or close, containing C, interval I containing C. And the following things are the vocabulary words that we'll be using from now on. So f of C is the minimum of f on the interval I if f of C is less than or equal to f of x for all x in I. Right, so that just means, remember, f of C is the output value, the y value at C. So it just means that y value is the lowest value that the function takes on that interval. Okay, because it's smaller than every other x on that interval I. And f of C is the maximum of f on the interval I if f of C is greater than or equal to f of x for all x on that interval I. Okay, so again, the output value basically is the maximum of that particular function f on the interval if it is bigger than every other output value, bigger than or equal to every other output value of the function on that interval. So further, the minimum and maximum of a function on an interval are the extreme values or often called extrema of the function on the interval. This also has another name for it. So the minimum and the maximum of a function on an interval are also called the absolute maximum and absolute minimum, or some books also use the so-called global maximum and global minimum. So if you go, let's say, on Chegg, right? If you go on Chegg to get help for this class, or you go to tutoring, or you go on the train, and somebody tells you to find the global maximum of a function on an interval, let's say 0 to 3, Now you know that that just simply refers to the maximum of the function given on the interval given. So let me draw an example. Let's say, for example, you're given the following. Say this is -1. Let's say we go from -1 to 2. Let's say you go 1, 2, 3, 4. And let's say we have the following. So we have a function that goes like this. And let's assume up here we have 5. All right, so if we're talking about the closed interval, so here we're talking about the closed interval -1 to 2. And notice that this function is continuous. There's no breaks between it. It's a continuous function. This function has a maximum and it has a minimum. The maximum value happens at which point? Well, the maximum value happens at the point 2, 5 up here. So f has a max at 2, 5, at the point 2, 5. And f has a min. So when I write max and min, I just mean the maximum and minimum. So it has a minimum. Where does it have the minimum? Well, if you said -1, 2, you are what we call wrong, because that's actually not the minimum of the function. The minimum happens down here. And that value happens to be 0, 1. So this function has a minimum at 0, 1. So it's not the lowest piece of the interval, it's the lowest point on the outputs. So we have a minimum at 0, 1 and a maximum at 2, 5. And that is for this closed interval, -1 to 2. Now what if we're given the same function? Okay, we're given the same function, so it kind of looks like this. Yeah. But now at the endpoints, I don't want to do that. At the endpoints, we have open circles. Oh, come on, don't do that to me. Okay, so at the endpoints we have open circles because our domain now, or our interval, instead of being from -1 to 2, is now from -1 to 2, but without the endpoints included. So we are not including the endpoints here. Well, if we do not include the endpoints, then f does not have a maximum nor minimum. Well, no, it does have a minimum. It doesn't have a maximum on -1, 2. The reason why it doesn't have a maximum is because since this point is open up here, then we know from the limit, that from the idea of the limit, that we could find infinitely many amount of points that get closer and closer to 5, but that are actually not equal to 5. So if you say, oh, the maximum is 4.99999. Well, you know that that's not true because you have 4.9999999. So you could find a number that is bigger than the one prior always, and that goes on forever, and you'll never actually reach the 5. So there's actually no maximum, but the minimum is still the same. The minimum, it's still the minimum is still 0, 1. Okay. So this 0, 1 refers to this point 0, 1. Maybe I should use a different color. Yeah, I'll use a different color. And then this -1, 2 refers to the actual interval. Finally, let's do one more. y. 1, 2, 3, 4, and 5. Minus 1, minus 2, no, minus 2. Alright, so how about this one? So let's say now we have, again, the same function, but now we have an open circle at the point 0, 1. So 0, 1 is not part of our domain. And now, so this interval is, again, minus 1 to 2. It's a closed interval. But notice that here x is not equal to 0. So here f has a maximum. It's a maximum at the point 2, 5. Is that what I put up here? Yeah, the point 2, 5. However, f does not have a minimum. And the reason for f not having a minimum is the same reason why I didn't have a maximum in the previous problem, because this is not included. We can always find an output value that gets closer and closer to 1, but it is actually not equal to that 1. So they keep getting smaller, but they actually do not reach 1. Okay? Alright, so from these definitions, we get to the following theorem that's going to actually prove to be very, very useful. Okay, so theorem. This is called the extreme value theorem. Extreme value theorem. Okay, so it says the following. If f is continuous on a closed interval AB, then f has both a minimum and a maximum on the interval. This theorem proves to be very, very useful in math. For those of you who are going to move forward to study more mathematics, the extreme value theorem is going to be your best friend in some classes, because it's definitely going to prove to be very useful. Now, notice that the hypothesis of the theorem assumes that f is continuous on the closed interval. Okay, f has to be both continuous and it has to be on a closed interval. If this is true, then f will have a minimum and a maximum on that interval. This function up here is defined on a closed interval, but it is not continuous at 0, 1 the way that I defined it. That's why it didn't have a minimum. Whereas this function is continuous on a closed interval, so that's why it did have both a max and a minimum. The theorem, the extreme value theorem, guarantees this. So this is the beautiful thing about this theorem, is that it guarantees this. Okay. Now let's look. Actually, I'm gonna end this video here, and I'm gonna continue on the next one.